Polar area with two curves, part two. Let's get ripping. All right, this might look like a mess, but I've got this beautiful heart-shaped like curve, r equals 1 plus sine theta. And then I have this simple circle. In this case, it's just r equals 0.5, which is a way to say the radius, the distance of this radius is always 0.5. There's no theta value that I care about because it's always going to be 0.5. And what we want to do is we want to find all of this region trapped between these two, but I'm going to stop it right up there at pi over 2. Okay, so that's what I'm trying to find. And you have to kind of diagnose the situation early on in the problem because this is definitely very different than our previous area problem in the problem we did in our previous video. In our previous video, we had area trapped between the red curve and the blue curve, but that area was really attributed part of it to a span captured by the red curve and a different span captured by the blue curve. And so we just split it up into two different integrals, and life was good. The situation we're in now is definitely different, and that's what I'm going to emphasize during this video. Before we get too far, I want to address that intersection point because, as I stressed before, you have to get good at getting those intersection points. So ignoring anything else you might see in this situation, concentrate on how I got that intersection point. The formula for one curve equals the formula for the other. I decided to go the algebra route rather than the calculator route. And I solve this thing and I can get 7 pi over 6 or 11 pi over 6. And so I'm going to choose 11 pi over 6, but I'm going to convert that to negative pi over 6, and I'll show you why here in a little bit. But I'm saying the intersection point is negative pi over 6, and that should make intuitive sense to us because if I were to shoot a radius out in this direction, it definitely seems like it's at a trajectory of negative pi over 6 or 11 pi over 6. And by the way, my last radius that gets shot out would be at a trajectory of pi over 2. So now we don't have to worry about those radii. But we have to think about a new style on how we're going to do this type of problem because it's not like the type in the previous video. So in an unprofessional way, I've redrawn this situation. And I want you to think about our analogies from before. If I wanted to find area, I would shoot out a radius. I would actually shoot out an infinite number of radii and then accumulate their area. Well, if I shoot out this radius, I'm not getting any of the speckled region that I want. So that's no good. Well, if I shoot out this radius, I'm definitely getting the speckled region, but I'm also getting more region than I want. This one's too little, this one's too big. All right, but check this out. If I do a very weird version of segment addition and subtraction, this entire segment, which is too big, take away this part of it, which is too small, would leave me with this part that's just right. The segment that's too big, take away the part that's too small that I didn't want, it's not getting the speckled area, leaves me with the part that I care about. That's the concept we're going to do here. And so I'm going to unveil how it shows up in the actual calculus language. Using that analogy, that we're going to shoot out a radius, and this part we don't want, this part we do want. That's going to happen by doing the outer curves, or in other words, the larger one. Let me go back. When I do this segment addition and subtraction, this first radius is the radius that would go out to the outer curve. Okay, but remember that was too big. This radius is the radius that would go out to the inner curve, and remember that's too small. But through the trick of math, we can get the one we want. So outer curve minus inner curve will leave me the distance that I want. We're now putting that into the math language. The area gotten by doing the outer curve is 1/2, then the outer curve's formula, squared. We're doing 1/2 r squared d theta. That's going to come at the end. Now I have to subtract away the inner curve. That's the distance out to here. R equals 0.5 is the inner curve. 1/2 r squared d theta. This was my beginning theta value, -pi/6, and it's going to go all the way up to pi/2. If I had chosen my 11pi/6, because remember when I did this with algebra earlier, we got 11pi/6. If I had chosen 11pi/6 for my beginning spot, that's 11pi/6, then I would have to imagine that I continue on and on and on and on until here. So if that's 11pi/6, 12pi/6, 13pi/6, 14pi/6, 15pi/6. So I would have to go, I don't even know if that's right. Let me think about that for a second. After careful consideration, I do agree with myself. Not surprisingly, people like to agree with themselves. 15pi/6. So this would be totally fine. You would get the same answer as we're going to get here. And now, as long as you could type that thing into your calculator without making a mistake, and good luck with that, you have the area trapped out here. Remember, a lot of times on an AP test, they'll have you write the integral, but they don't have you compute the integral. So be sure to diagnose the situation. When you have the area trapped between two polar curves, it could be this type of situation where one radius is too large and one radius is too small, in which case you use this style of thinking. But it could be the type of scenario that I was talking about on the previous video, where you don't have any subtraction needed with your radii, you just have two different parts to your calculation. That concludes the polar area with two curves.